Hi everyone, welcome. In this video, I'll talk about my architecture for banking fraud detection using AWS Sagemaker. Let me give a brief introduction about myself. My name is Thirumavalavan Srinivasan. I'm working as an architect at Wipro Technologies. I'm working at a client project for Hewlett Packard Enterprise on network attached storage domain. I have over 17 years of IT industry experience, and I'm also an APN ambassador for NAMER region. Currently, I hold 8 valid AWS certifications that includes AWS Certified Machine Learning Specialty. Let's see about the dataset. So it's the PaySim synthetic dataset of mobile money transactions. And here each step represents an hour of simulation. And we can download the dataset from the Kaggle location URL that I have given here. And we need to create an account on Kaggle and then we can download the dataset. So let's see about the features of the dataset. We have like as we already said, like we have step. It's a maps a unit of time in a real world. In this case, it's one step is 1 hour of time, and we have a type that is various type of the transaction, that is cash in, cash out, debit, payment, and transfer, and then amount of the transaction in local currency, and customer who started the transaction, and initial balance before the transaction, and the new balance after the transaction, on the customer account, and the recipient ID of the transaction, and the initial recipient balance before the transaction, and the recipient's balance after the transaction. So these are the features, the columns, and then we have two classifiers that label. One is fraud, and then that identifies a fraudulent transactions and non-fraudulent transaction. So it's one is fraudulent transaction, and non-fraudulent transaction is marked as 0. And we have another label that is flagged fraud. So it flags illegal attempts to transfer more than 200,000 in a single transaction. So let's see the various steps that involves here. So we use AWS lake formation, and glue and Athena and QuickSight for ingesting and visualizing and storing the data. First, we have to download the data from the Kaggle Kaggle site. The URL is given here, and then that dataset is uploaded to an S3 bucket. And for AWS lake formation setup, it involves 3 steps. First we need to create a Amazon S3 bucket, and then we need to register that as a data lake location. And then we need to create a database in the AWS lake formation, and next we need to give the appropriate permissions. So once the AWS lake formation setup is completed, we can use AWS Glue. AWS Glue is tightly integrated with AWS lake formation. So with the AWS Glue, we can use the AWS Glue crawler to crawl the dataset that we have already uploaded to Amazon S3 bucket to infer the schema. So we can use the database created in AWS lake formation here, and then the AWS Glue crawler is going to crawl the dataset and then create the infer the schema, and then it will create a table in the database. Once this is done, we can use AWS Athena to query the database for exploratory data analysis. You can use AWS Athena. It's a serverless query, SQL query. So these are the AWS Athena queries that I have used for data analysis. We will walk through each query in the live demo next. So next, and yeah, these are the queries. Once that is done, we can use AWS QuickSight for visualizing. So QuickSight is is easy to create the visualization. Here we are seeing the records by date and the records by date and type, and next we see this fraudulent transaction by date and type, and the flagged fraud transaction by date and type, And here we are seeing the bar chart for records by type, and the fraudulent transaction by type, and fraudulent transaction for flagged fraud, and then the pie chart here, and we can create the heat map, stocked area map. So once the visualization is done, we can use AWS QuickSight for anomaly detection. So this is powerful. This uses machine learning powered insight. To create the insight for anomaly detection, we need to use AWS QuickSight Enterprise Edition. Unfortunately, the insight for anomaly detection is not available on QuickSight Standard Edition. So we are using AWS Enterprise Edition for QuickSight. And currently in our data set, we don't have a date field, date column. We have step that represents 1 hour. One step represents 1 hour of the time, but we don't have a date field. Without date field, we cannot do the anomaly detection insight. But AWS QuickSight offers a feature called calculated field. We can create a calculated field since the step column is already the representation of time in one step represents 1 hour. So we can use that use epoch date function and then pass in the step value. With that, if we multiply that 3600, we can get that date, epoch date. But that date, whatever it is producing, is the first epoch date, like that's 1970 January 1st. So what have done is I have added this value here. This value is nothing but epoch date for December 1st 2020. So with this date added, we can get a visual value, representation of that the data captured as if it is captured in December 2020, like from December 1st to December 31st 2020. We can see that here in the visualization also. Here it says like December 1st to December 31st 2020. Once the calculated field for date is created using epoch date function, we can go ahead and add insight, and then here we can select anomaly detection, that is ML powered insight. We can select that. Once that is done, we need to provide the fields, fields for the anomaly detection. First one is the time field, that is in a date. So we have already created a calculated date field. Then we can pass in values, amount as values, and then we can pass type for the categories. Once that is done, we can run the anomaly detection. It takes hardly a couple of minutes to do that. We will see that also in the AWS QuickSight console later. Here we can see that QuickSight anomaly detection. Once that is done, next we can use AWS Glue jobs to transform the data set. We can drop the fields like a name original and the name destination and is flagged fraud columns, and then we can use data lake location to ingest the data to the AWS data lake. We can use the Glue job to do that. Once that is done, we can use AWS Sagemaker algorithms for our architecture. So here we are using 3 AWS Sagemaker algorithms. The first is a random cut forest. It's unsupervised algorithm. We can use a random cut forest to see if we can detect the outliers, and then if that is marked as fraudulent or not. Here is the evaluation for the random cut forest. We can see that the outliers are already marked as fraudulent one, the blue line. Next, we will use XGBoost. So this is the evaluation for the base model for XGBoost. We have a good recall, that's 97%, and precision is 71%. F1 score is 82% for fraudulent classifier. And we can go ahead and see the result for the uh, oversampling technique what we use. So we can use SMOT for oversample the minority data, the fraudulent cases, and then once we do that, our recall is increased to 99%, and precision is dropped to 22%, and the fun score is 31%, and that area under the curve for ROC curve, it's 99%. The reason why we have this value is increased here, so for that false positive, that's because we have used smart for oversampling the minority, the fraudulent cases. And we can also use, we have used automatic model tuning for hyperparameter tuning. So here is the evaluation for that model that we used for automatic model tuning. And our recall is still at 99%. Precision has increased to 31%. F1 score is increased to 47% after using hyperparameter tuner for smart model. Next, this is the evaluation for the linear learner base model. And linear learner base model gives good precision, that is 98%, but the recall is at 10%, and F1 score is 19% for fraudulent classifier. And if we use if you optimize the linear learner model for a recall, but still the recall has not increased, it's because our data set is highly imbalanced. We have more non-fraudulent cases and a few fraudulent cases. So what we can do is we can use the balanced model for a recall. Now that ROC is increased, and then our recall is 90%, and then precision is dropped, and then F1 score is also dropped. And we can see that, like evaluation for the linear learner model for smart, we can use the smart to oversample the minority data, and then we can use once we use it for the recall, we have a 93% for recall, but still precision F1 score is dropped. So we have to take a call, like if we want to catch all the fraudulent cases, or is it fine if we can slip through some of that. So in ideal scenario, we would want to maximize the recall, but here if we try to maximize the recall with the linear learner model, our precision is dropped, that we are going to give a lot of false negative, and then that is going to give unhappy customers. If we see that, like compare both XGBoost and linear learner model, XGBoost gives a better performance for for both precision and recall. So it's for our given data set, XGBoost does better. Thank you. And next, let's see the AWS console. We see the AWS SageMaker, and let's walk through the architecture. Thank you. Hi, welcome back to the live demo for banking fraud detection using AWS SageMaker. And here is the Kaggle link, and here is the download link. We can go ahead and download the dataset. I already downloaded the dataset and uploaded to AWS S3. Here I have created a bucket named AAMLBB capstone and prefix banking fraud and input dataset, and I have uploaded the dataset here that is downloaded from the Kaggle link. Now let's go to lake formation. And for lake formation setup, we have 3 steps. Step 1 is to register Amazon S3 storage location and create a database and granting permission. I have done all 3 steps, and I'll show you here. I have created a bucket named Thiru AMLBB data lake, and then linked that as a location for data lake location. And then I have created a database named data lake DB, and have given the permissions, the necessary permissions here. So once that is done, like we can go ahead and use the data crawler. This is nothing but the glue crawler. I have already created a crawler job. Um, this is to crawl the banking of our data set, and this is the location I have uploaded the data set which is downloaded from the Kaggle location, and then it's this one inferred the schema and then created a table for the database, that is data lake DB and table. So this is the table, and then we can see the schema here. Like it has inferred all the schema, like the column name is step, type, amount, name original, and etc. Is fraud and is flagged fraud. All the fields has been inferred here successfully. Once this is done, like we can go to Athena to query. So here we can select the data catalog and then select data like DB, and I have already written down the queries here. Let's go ahead and run. This is just to check the first 10 rows from the data set, and it is inferred everything correctly. All the columns looks good. And next we can run this query to see the total count. Actually we have over 63 million records in our data set. And let's see the fraudulent transaction count. So if you see non-fraud is almost 63 million, and then we have only 8,213 fraudulent transaction here total. And then we are seeing the fraudulent transaction as a percentage. We have 99.87% is non-fraudulent, the genuine transaction, and we have 0.129 like approximately 0.13 percentage of fraudulent transaction here. Let's see how many transactions are flagged as fraud. We have only 16 transactions that is flagged as fraud. And if you see the percentage wise, the 16 with respect to the 63 million transaction, it will be very minimal. And here we are seeing the transaction type where the fraudulent transaction has occurred. We have cash out, like 4116 transaction as flagged as fraud. And for transaction type transfer, we have 4097 transaction that is flagged as fraud. And if you see the transaction that is flagged fraud, that also happens in transfer. Everything else, we don't have any all genuine transaction here. Let's go ahead and run another query. Let me copy that over here. So here we can see the transaction that is flagged as fraud. So we have 16 transaction, all 16 transactions that is flagged as fraud. If you see, all those transactions are also flagged as fraud here. So it's like we can safely drop this column, and then we can just use only the is fraud column as the label for our predictions. And another one. So we are just seeing that distinct count for the name destination field. We have around 27 million distinct names for the destination name field. For name original, like the customer who initiated the transaction, if we see, we have almost 63 million unique names for the name original. And now if you see this, if we see the name original count, which is unique and which is marked as a fraud, that is 8213. That's the total number of fraudulent transactions that we have. So name originated, the customer who initiated the transaction doesn't make any sense. We can drop this column as well. And for the name destination field, if we see like the unique names and that is marked as a flagged fraud, it's almost 8169 names we have as unique names, that is distinct and then marked as fraud. And so we have approximately for 40 or 44 transactions that duplicate names are available here, but that is very insignificant. We can go ahead and drop this column as well and see how our model behaves with this. So now we have done the data analysis through AWS Athena. Let's go ahead and visualize, see it in visual using QuickSight. So here, if you see, like I have already created some of the visual graphs. So this is for count of the records by date, and then records by by date and type. Here you can see the transaction for each date and for each category. And here we'll just have that sum of it, like how many transactions happened in each day. And then if we can see that, like the fraudulent transaction by date and type, and is flagged fraud for date and type here. And then the bar chart for the records by type, and that the fraudulent transactions by type here, and then flagged fraud by type, and then the pie chart for the records by type, you can see. And then we can see like how many percentage each transaction type contributes in our data set. And then the fraud by type, and here we have like almost like 50 percentage, and then the heat map for fraudulent transactions by type, and date and type for the fraudulent transactions, and then stack data chart here for fraudulent transactions date and type. So next we come to that anomaly detection. So we have already detected that anomaly. Let's go ahead and explore that, and I'll show you how we have created that. So we can see that anomalies by date. We can see that anomalies by date, and I'll show you how I did that. Like if you go to dataset, and this is the dataset that I have imported directly from S3, just named it as banking fraud. If I edit the dataset, I can show you. Here is the date field. This is the calculated field that I have created from our step here we have step, and then from the step we have created the date column. And if you see the calculation for date, I have already explained. I used the epoch date function, and then use the step value and then multiplied by 3600. That gives that epoch date for 1970 Jan 1st, and then we can add the epoch date for December 1st 2020. So just to give a assumption that the data is collected from December 1st to December 31st, because the date field is needed for creating for anomaly detection. Let's go back, and then I'll show you how to do the insight. Here we can click on add insight, and we can select anomaly detection, select it. Once we select that, here go to field wells, and we need to add a dimension. It's a time, we need a date here, add a date, and aggregate it by hour, because our data is collected every hour using the step value. And here for value we can give amount of the transaction, and we can see the type for the category here. Once this is done, we can say get started, and everything looks good. We can use analyze all combinations of these categories and save, and we can run. This hardly take couple of minutes. So we have already completed that here, and the inside we already completed that, and then explore the anomaly here. So that's about visualization and anomaly detection using AWS QuickSight. Now we can go back to Glue and then create a Glue job to ingest the data to the data lake. I have already created a Glue job, data lake ingest job, and this is already completed and successfully. And what it does is it reads the when you know the data from the database, and then ingest into the S3 bucket. When we do that, I have dropped the columns for name original and name destination and is flagged fraud. These three columns we can drop it, and then write it to data lake location in CSV format. Let's go to S3, and this is the bucket that I have registered with data lake. And if you see its location, Glue transformed dataset. So here it is AWS Glue job ingested the data in multi-parts in CSV format, and this is what we are going to use for our further AWS Sagemaker analysis. So we are done with the AWS data lake, Glue, Athena, and QuickSight. Let's move into AWS Sagemaker, and I have already created a notebook instance, that is YAML M5X large. I have executed the random cut forest and XGBoost and linear learner models on M5X large instance. I have the instance open here. Let's first go to random cut forest. So here it's the notebook is mostly self-explanatory. I have given enough comments here. If you go here and like what is needed, like install the needed libraries first, and load the needed libraries, and then load the data set from the AWS lake formation. You can see this script goes and reads all the files from AWS data lake, all these files, and in Panda library it creates a data frame, and then we can clean and analyze, transform and prepare the data set. Here we are seeing, the data type and everything, and uh, we are seeing that, correlation and statistical analysis for the numerical data set. And we have to one hard encode the type column here. Type column is not a numerical column. It's if you cash in, cash out, debit and the transfer, it has a different values. So we need to one hard encode using a panda get dummies library. Once that is done, we have to create a feature and label column, split it, and then use convert that on numpy array. Then we can run the training. We are actually, yeah, and we are using managed spot instances for the training here. um, Here if you see, like, managed spot training savings, we have 61.8% saving since we used the managed spot instances for our training. The original training seconds, it's 76, but it's billable only 29 because we have used the spot instance for the remaining time here. And we can just use the deploy method to deploy the random cut forest model that we have created, and we can test it out. And if we see the positive negative scores, the unsupervised model, it's achieving some separation between the classes, the fraudulent and fraudulent classes. If you see the ones that is with the higher anomalies, already marked as fraudulent here. So this is about random cut forest. Let's go to XGBoost. Yeah, here we have all the steps outlined here. How we investigate the process the data, load it from the data for lake formation, and then clean and transform it, and then one hot encode standardization using standard scalar, and XGBoost supervised training the base model. For that, like, how we prepare and upload the data to S3. We convert that training and validation data set, split that data set into training, validation and test, and then converting it to libsvm format that is supported by XGBoost, and then use managed spot training, and how we deploy the model and how we do the evaluation, and how we use that smart for oversampling the minority data, and then how we can deploy the smart model, and how we are using automatic model tuning for hyperparameter tuning, and how we can deploy and then evaluate the model, and all those things. Let's quickly run through it here. This data, and then import the libraries here. This is similar to the previous model here. We just prepare the data and then one hot encode it, and then create feature columns and label columns, separate it out, and then split the data set into training, validation and test, and then convert it to numpy array here, and then standardization using standard scalar here, and then upload it S3 using libsvm format here. And then the hyperparameters that are used, and then we explained it as well here, and then we are using managed spot training as well here. Let's see how much we have saved. We are using this spot instances set to true here, and then we are using the spot instances here, and then we are running the fit to train the model. Now we have saved around 62.6% due to the managed save spot instances here. I can deploy the model and then run the evaluation, and we can see that we have already saw that in the presentation slides here. So the recall value for fraudulent class classifier, and the precision value, and our ROC area under the curve, that's 98%, looks good. And we do the smart here to oversample. After the smart we can standardize it again and train the model. And with the smart we saved 61.5%, that's good. And now we can deploy and then run the evaluation. And here we are doing automatic model tuning. To tune the hyperparameters, we have selected eta, min, child weight, and alpha and max depth, and the range of values that we have given here. And we have set the objective metric as validation area under the curve, and run the model. It takes almost 6 hours to get it completed, because we have oversampled the data using a smart, and then we are running 20 jobs and 3 in parallel. So we are using Bayesian strategy for hyperparameter tuning here. And once that is done, we can deploy the model. And when you run the evaluation, we can see the recall, precision, and F1 score. Once everything is done, we can run this cell to delete the model and the endpoint. We have to uncomment that if we need to delete it. That's about XGBoost model. Let's go to linear learner model. So linear learner model, also we have created 4 models, one base, and then the second optimized for recall, and third we are optimized for balanced recall, and then the fourth for using the oversampling smart method that we can see it here. Investigate data, load the data set, clean transform on hard encoding, and creating and training linear learner model. This is the base model, and then evaluation here, and then optimize the linear learner model for recall, and this is for evaluation for recall model, and then optimized linear learner model for balanced recall, and then for smart. Let's go to here, creating and training linear learner model. We are splitting the data set 64% for the training, 20% for the validation, and 20% for the testing here. And we are creating record IO protobuf converting the data into record IO protobuf format, so we can use the pipe mode when we use the training. And here it is running. We are using managed spot instances wherever possible, and we are running 20 epochs here, so we have saved around 53.7%. And we can run the evaluation here, and this is for the model for optimized for recall, and this is for optimized recall for balanced recall. So if we can see here with the hyperparameters, we can say it's balanced for recall, and we are seeing precision at target recall, and target recall is 9.9, that is 90%. End of this model, if you see, our recall is 90%. And now we are using oversampling using smart, and we are using the standard scalar as well to standardize the data, converting the data into record IO protobuf. And here we are validating that model. So we can delete the 4 models that we created and edit the endpoint by uncommenting and then running this cell. With this, our XGBoost model looks better for both recall and precision and F1 score for banking fraud detection. Thank you.